Syzygy, episode 19, Exomoons and Exomoonmoons. Yes, indeed. Welcome back for another episode of Syzygy. Syzygy 19. My name's Chris Stewart, and joining me at the microphone, as ever, is Emily Brunsden.
Hello, hello.
So in this episode, we're going to be talking about moons.
Moons.
Yes, indeed. All sorts of different kinds of moons. Exomoons.
Exomoons.
Why are we talking about moons this week? Exomoons.
Exomoons.
Talk to me.
So, well, we've talked before about exoplanets. So these are planets that go around stars or that are out there in the galaxy that are not going around our own sun.
Yeah, and we have talked about this a bit before because we are avid fans of the TESS satellite, the Transiting Exoplanets Survey satellite, which is one of the latest bits of stuff up there orbiting around in space, looking for exoplanets, doing a survey of the night sky and finding lots of things orbiting distant stars. So we're getting a bit used to that now. It used to be that exoplanets were, hey, we found an exoplanet, this is really exciting. And now it's still a very cool thing, but we have a lot of them. Exomoons, though, not so much.
Yeah, a new first. New first. So this discovery was actually made with the Kepler space telescope. So this is kind of TESS's predecessor, the famous planet hunter, the one that we have thousands of exoplanets from. And digging really deep into the Kepler data.
Well, now hang on. Is Kepler still going, or is this data that we've already got and digging into?
So this is data taken between 2009 and 2013, because after that Kepler got a little bit hamstrung by some reaction wheels failing. And actually very recently it really does sound like Kepler actually is properly dead.
Oh dear.
So I think we just need to have a moment's silence for the wonderful spacecraft that was Kepler.
Kepler, you'll be missed. That's very sad. Hey, didn't something similar happen this week with Hubble as well? Didn't something go sproing inside Hubble? And
yeah, so some of Hubble's gyros are not working properly. Now, that's not so much of an issue. Gyros are used to help the pointing and stability of the spacecraft, but actually Hubble can work with no gyroscopes if it needs to. So it's probably going to be okay, is really the outcome of that.
I mean, Hubble's done pretty well. It's already gone past its mission specifications, hasn't it?
Yeah, many times over. So, but we still love Hubble. I mean, we'd really want Hubble to stay until at least we have James Webb.
Yeah, we'd really rather that not go away. And James Webb, we're rooting for you as well. Come on. Okay, anyway, getting back to the story.
Yeah, Hubble was involved in this discovery as well, actually.
Right, cool.
So it really is still a very useful scientific instrument. So, well, it was just, as I say, it was discovered in the Kepler data that there are lots of exomoon candidates that we've known about for a while, because, it doesn't make sense that in all these extra solar systems, if you like, that they wouldn't be similarly set up as ours.
And in our solar system, we do have a lot of moons. I mean, we have ours, and Earth has one. But there are plenty of others. In fact, are there any planets that don't have moons?
Mercury doesn't have a moon.
Mercury doesn't. Does Venus?
Venus doesn't.
Okay.
No. So.
But Mars does. Mars has got a couple.
Has 2, yeah.
And Jupiter's got like
more
loads.
Than 60, heaps.
I mean, that's just rude at that point. You're just getting greedy. And Saturn's got loads.
Yeah.
So moons aren't rare.
No, they're certainly a normal part, if you like, of planet formation is that you expect to have moons as part of your solar system.
So it wouldn't be surprising if we did find exomoons around exoplanets. But I guess by their very nature, they're a bit harder to see.
Yeah, well, think about how difficult it is to find exoplanets because they don't put out any light of their own. We're reliant on these kind of secondary effects that they have on other objects. So yeah, it's really, really tough to get exoplanets. So it's insanely tough to try and find exomoons.
So in this particular story then, and sorry, who are we talking about here? Who's done some work?
Yeah, this is some really cool stuff that's come out of Columbia University by Tichy and Kipling, and they published this article in the 3rd of October. So, just
very
really
recent, just the other day.
Okay. Super cool.
And what have they found?
So they have found that there is a planet that's orbiting a star in the Kepler field, which appears to have a moon going around it.
Right.
Now, there's a little bit of we think this is the best answer. there are hints of this in the data, and we're going to talk about the two different types of data that they're using to determine this. And they're saying, well, we've tried every other explanation that we can possibly think of, and the one that we're left with is that it's an exomoon.
Right. I mean, with these things, as you say, you're never seeing them directly. We're not training a big telescope on the distant star and saying, there, see that bit there, that little dot there, that's the planet. We're looking at things like transits across the star and dimming and brightening of the star's brightness and those sorts of things. And so the data that they're collecting, you need to be able to throw models and ideas at that to be able to say, well, okay, this is a bit different. What would explain this? And what you're saying is, well, one decent explanation at this point is it's a planet with a moon, which is very cool.
Very cool. And it's also nothing like anything we have in our solar system.
Oh, okay.
Which is always exciting.
All right. Okay. So how do we start to unpack this?
Okay. Well, let's talk about the planet.
Okay.
So the planet is about the size of Jupiter.
Mm-hmm. So
Okay.
it's big.
It's big. Fairly standard sort of Jupiter-ish planet, except it's about 10 times the mass of Jupiter.
Right. Okay. So big.
Big, yeah. But the moon is about the size of Neptune,
Which is still pretty big.
which is really big.
Yeah.
Right.
How big's Neptune in comparison with, say, the Earth?
So Neptune's about 4 times the radius of the Earth.
Right. Okay.
Yeah. So
And
it's about
Jupiter's-
17 times heavier than the Earth.
Jupiter's much bigger than that. And so this exoplanet is much bigger again, but we're talking big thing orbiting even bigger thing. So if you are going to discover an exoplanet with an exomoon, it seems reasonable to expect that they would be big.
Yeah, I mean, the big things are the easiest things to find.
Sure, okay.
Because they have the most impact on both of the types of data that we're going to be talking about.
Now, none of Jupiter's moons are anywhere near that kind of size, are
No,
they? They're all
no.
quite small.
They're all much smaller than the Earth. So
is that what you meant when you said a second ago that this is unlike anything we've seen in our own solar system?
yeah, it's kind of like if you took Jupiter, stuck Neptune around it.
Which is possible because Jupiter's big and Neptune's big, but there's nothing incompatible with, theories of things going around other things that says that couldn't happen. But it hasn't. Well, we don't have that in our solar system.
And it starts to make us think, and particularly I got really thinking about this. Well, is this a moon or is this a binary planet?
Oh, okay. Yeah. I mean, when does one end and the other begin?
Yeah.
Is that even a thing?
I don't really know.
All right. So let's develop this one step at a time.
Yeah.
So first of all, how did they find it? What talk me through the data.
So Kepler was this wonderful telescope that stared at a patch of the sky in Cygnus for over 3 years, just looking at about 100,000 stars. And in that field is this star. It's called Kepler 1652.
Another good name.
Yeah. And around that star, it was fairly early on in the Kepler mission, we were able to see that it had a planet going around it because we saw this periodic dropping of the light coming from this star.
So this was a fairly bog standard style. Here is a star. We see its brightness dip, therefore planet.
Yeah.
Okay.
And it's got this Jupiter-sized planet. It's sort of kind of a hot Jupiter, but not quite, because it's about the orbital distance of the Earth away from the star.
When you say a hot Jupiter, do you mean a Jupiter which is almost turning on to be a star, or do you mean a Jupiter which is quite close to its host star? Or
quite close.
Right.
So we found a lot of these big planets that are very, very close to their host stars. So this is a little bit kind of further away. Jupiter's about, as I say, where the Earth's orbit is, and the star is very similar to the sun as well. So actually, we've got some good comparative objects in our solar system to see what these things might look like.
Okay.
So it actually has quite a long orbit, therefore, because if you put something out as far away as the Earth's orbit, then it takes nearly a year to go round, 287 days. So we only managed to capture with the Kepler Space Telescope 3 transits in its lifetime.
And you said that this was found fairly early on in Kepler's data taking. So I'm guessing that when it was first seen, it was, hey, exoplanet, fantastic. Was it noticed at the time that there was anything different?
Not quite initially, because as the Kepler mission progressed, we actually got much, much better at the processing of the data that comes off the telescope and the way that the telescope reads that data back to us as well. So I had a look at these transits, and you see all 3, and actually the third one is much, much more clear. And that's just us learning how to deal with the data better.
You get better as you keep trying. Yeah.
So by the time we got to the third one, and if you put those three together, you can sort of put them on top of each other, and you can start to look for things that might be different about this system. And this system did sort of maybe kind of have a hint that there might be something in the transit curve, but it was all really buried in the noise.
What? So like a transit curve, the brightness dips, but it doesn't necessarily dip in a really simple way. There's a bit of structure there. There's something interesting maybe going on.
Yeah. Well, for a moon, you'd expect a second dip,
right?
For example,
right. As the moon comes around the planet that it's orbiting, it's, it also blocks a little bit of the light, or as it disappears behind the planet or in front of the planet, then the brightness of the star goes up a little bit or down a little bit. So yeah, there's a bit more structure to that curve than you'd expect.
But actually, really what kind of threw everyone into looking that this might be actually an exomoon system was something called the transit timing variation. So we know that when a planet goes around a star, it has a period. So it goes around, in the case of the Earth, every 365 days, and in this case, every 287 days. But actually, the exact timing of that period can change. And so this is called the TTV, transit timing variation method. And we've actually used this to discover lots of planets. Because if your transit happens a little bit earlier or a little bit later than you expect it to, then that's an indication that something's been gravitationally tugging on your object and changing its orbit a little bit.
Okay. So what you're saying is that if the timing changes, then that means the orbital period, the orbit of the planet has changed, which implies there's something else you haven't seen yet.
Yeah.
It's not just star and planet, it's star and planet and probably other planet or planets as well.
And in the case of this one, it was about 78 minutes early to transit. So you think, oh, okay. That's interesting.
Which is not a lot on a 287-day orbit, but on the other hand, it is a lot because these things are normally pretty periodic. So,
I mean, imagine if our year changed by more than an hour every year. That would be weird, right?
Yeah, we'd notice that. Yeah. So what does that mean? Does that mean another planet or what?
It can mean another planet, and that possibility has not been completely ruled out yet. And so, but this was a good candidate to follow up to say, well, it could be another planet, but it might be an exomoon. So let's look at this a little bit in more detail. And that's exactly what this pair did. They went and got Hubble time. And Hubble time is really hard to get, right?
Hubble time sounds like a song from the 90s by some American rapper, but anyway.
So, well, it's difficult because everyone wants time on the Hubble Space Telescope, but they really got quite a lot of time on Hubble. They got more than 40 hours. And so they knew that when the next transit was going to be, plus or minus an hour or two. And so they asked Hubble to look at it during that time. And Hubble has a much, much better aperture in terms of looking at this. It's got a bigger telescope in it, basically, and you're looking and you can get higher precision on your light variations, as well as get some kind of color information.
Right. So Hubble's not great for doing a survey because it's much more precise than that. So Kepler's great for looking at a whole bunch of things and trying to find, amongst all of these stars, which are the ones which are having variation. And then you can turn Hubble on it and go, no, that one there, let's have a really good look at that, which Kepler can't do.
Yeah, well, certainly can't do anymore anyway.
Well, yeah, moot point, but couldn't do.
No.
They're
designed to do different things. Hubble's much better at looking at a single target. So they looked at the Hubble data. They got another transit. They got much, much higher precision on the transit itself, which was really cool. A lot of work went into this, like crazy amounts of work, just getting the data and getting it as precise as it can possibly be. It's really impressive what this group have done. And they managed to see this transit, and again, even maybe a little bit of the transit of the moon. So there's a little kind of signal in there. You kind of got to squint and look a bit sideways at it, but yeah, okay, maybe it's there.
So it's not absolutely definitive, even though, as you said, it's incredibly precise and accurate data. It's still not entirely definitive to say, that bit there, that's a moon. So where does it sit then? Is there still hypothesis?
Well, I remember that we're talking about super ultra precision. Like this is the Hubble data, for example, was looking at errors of maybe 300, 400 parts per million. So this is fractions of fractions of fractions of percentages.
Okay, so that's good.
That's amazing.
That's really
really
good.
amazing.
But I guess the question is, how definitively can we say that's an exomoon?
So that's where we need the models to come and help us, because what you want to be able to do is you say you've got these two pieces of data. You've got the transit timing and you've got the transits themselves from both telescopes. What is a model that we can generate that's going to fit all the data in the best possible way?
So what you're saying is, just to back up a second, it's only just clicked in my head. You said a second ago this is incredibly precise data. So what you're basically saying is, look, the experimental people looking with these telescopes are going, this is as good as we're going to get. This is really good. There's no doubt here. So you guys now figure out what's going on.
Yeah.
Because we're not going to get better data than this at this point. Go do some modeling to figure out why this looks this way. Mm-hmm. Gotcha. Okay.
And so they tried different models. Yeah. So they tried like a model which just has the planet. They tried a planet that has a moon that you can't see, so it wouldn't cause a transit. They tried
what would be a moon you can't see?
So, well, one that's not changing the light in the transit curve, let's say.
Okay.
So it didn't have any impact on the brightness measurements.
Like too small or going in the wrong direction?
Yeah, or behind the planet.
Right.
Well, whatever.
Gotcha.
It was too, yeah.
Okay.
Models that looked at that, models that had two planets. So, what lots of things. These are all the possibilities we can possibly think of. There's a model, what that might look like if we were to make measurements of that system, and then which is the one that fits the best. And it turns out that the moon model fitted the best.
Cool. By a long way, or sort of ahead by a nose?
Statistically significant.
Okay.
Yeah.
Enough to say this could be the real thing.
I think, this is probably the best we can do with the data that we have, is really the conclusion there.
Cool. Now that model, presumably, would be factoring in, well, we know pretty well the size of this planet. You said it was sort of Jupiter times 10 in mass. But I'm guessing that model also has a parameter in it, which is, so how big's the moon? And this is where the Neptune-sized moon comes in.
Yeah. I mean, none of these values are 100% certain. In fact, masses and radii of planets are really hard because you need to know data about the star very accurately, which we sort of do, but it's not an astroseismic star, so we can't get the most precise data we want out of it. But it's pretty good.
So to within reasonable error bars,
yes,
we think that this is what this looks like.
Yeah. And when you think about how these systems might form, okay, there's no real planetary formation model or theory that can tell you that you're going to form a Jupiter and a Neptune next to each other. But we know that that's not the only way you can make a system like this, because captured objects are really common. I mean, in our solar system alone, we know that the Earth captured the moon, for example, or got blown off and part of the Earth became the moon, or something weird happened there.
Yeah, we need to talk about that at some point, because I keep reading bits and pieces about the moon's origin story. And for someone who grew up just sort of, never really questioning it and thinking, oh, it's just the moon, it just came from the more you read about it, the more you think that's a great story. That's pretty amazing. So we can come back to that another time. But as you say, it's not just a matter of the moon having formed at the same time as the Earth, and that's just what happens. It was something much more interesting than that, and it got captured. Yeah. So that's normal. Yeah,
that's Mars's moons are captured asteroids. Basically, they're just little lumps look like potatoes. Triton, Neptune's moon, probably came from the Oort cloud, which is what we talked about last week. So, it's fairly common for things to have come from maybe completely different places in the solar system and to wind up orbiting each other.
So the idea of a really big Jupiter capturing a Neptune, not so crazy. They could have formed completely separately and then just wandered within each other's gravitational influence in the right way to go, I'll have that. Thanks very much. You're now mine.
Yep.
Cool.
Not implausible at all. So that's quite cool.
It really does beg that question, though. Like, is it a moon?
Yeah. That's what I start thinking. And, here I have to make a huge confession.
Okay.
And that is, astronomers have not been very good at classifying things in the last 100 years or so.
Yeah. Careful. I don't want people to start writing in and complaining, Pluto. But we are kind of going down this track, aren't we?
We've got one definition that's very precise.
Okay, what's the good one? Let's lead with that.
So we know very well what a planet in the solar system is.
Okay.
We have a definition for that was laid out in 2006 that everyone's in broad agreement with.
And there were 3 components to that, weren't
3
there?
components.
Okay, so
Here's your test.
Okay, let me see. Have I been paying attention? So, big enough to be a sphere.
Yep.
Yep. Okay, so it's got to be big enough so that the mass of the planet compactifies it down into a spherical shape, which is what gravity will do when you're above a certain size. So
Yep.
it's got to be big enough to be round. Good. Excellent. It's got to have cleared its own orbit.
Yes.
So as it's going around the sun or its host star, it's got to have just knocked everything else out of the way as much as humanly possible. So in other words, there aren't a bunch of other things of, comparable-ish size going around saying, no, this is my orbit. No, it's the planet's orbit. The third one.
This is kind of the easiest one.
Is it?
Yeah.
No, I've got nothing. What is it?
It's got to go around the sun.
Oh. Well, I was taking that as a given, Emily. Sure. Okay, so it's got to be going around the sun, or it's got to be going... Right, okay. Going around a star and spheroidal and cleared its own orbit.
Okay. Now I'm going to ask you a question.
Yep.
How do you define an exoplanet?
It's all of those things, but not around our sun, around a different star.
What about rogue planets, though? They're these planets that are free floating. They don't have a little star to go around.
Oh, no, okay. Fallen at the first hurdle. So I would guess that rogue planets are pretty large lumps of rock that aren't going around other stars, but are wandering free. But do they have to be spherical? They haven't got orbits.
Yeah.
Help me me here.
I can't, because we haven't defined officially what an exoplanet is.
Right.
We have common sense definition, right? Which is we know when we see one.
Yes, exactly. I don't know what an exoplanet is, but I know it when I see it.
Yeah. But no, we don't have an official definition. And part of the reason is because it comes really hard, actually. To form.
Is it one of those things where the more you think about it, the more you come up with other examples, like you just did with the rogue planet thing? Other examples of, but what about these? I mean, what's the difference between a rogue planet and just a lump of rock in space? I don't know.
Yeah. But we can come back a little bit and we can say, well, we do know pretty well what a star is, right?
Okay.
At least
good, because
sort of.
if we can't do that one, I would have thought I'd just walk away at this point and hand it over to the astrologers, don't you? Isn't that the thing that defines astronomy, is we know what this stuff is that we're looking at?
But isn't it wonderful that we kind of don't?
Sure, let's go with that. Okay, so we're pretty sure at the 95% level we know what a star is.
We know what a star is because it's the thing that's big enough, it's fusing.
I'm losing faith, Emily.
Well, okay, it's a little bit tricky because actually we have these objects called brown dwarfs. Are they stars or
Fringe
not?
cases.
Is an open question.
Are they stars which aren't quite big enough to turn on, or did turn on but then turned off? Or what are brown dwarfs?
Okay, so a classical star, if you like, is going to be big enough to fuse hydrogen in the core. And that's what the sun does in all these wonderful objects that you see in the night sky. Now, brown dwarfs, it's really complicated. They're things that are between about 13 times the mass of Jupiter and about 65, 70 times the mass of Jupiter. Those limits are debated. Right. But about that size. So big Jupiter-y things. Now, they're big enough to actually have enough gravity to start fusing deuterium and in some cases tritium.
Right. So they're big, the gravity's pushing down, squeezing down in the core. It's incredibly hot and dense, and there's enough squeeze there that something is happening nuclear-wise. There's some fusion going on, but you're about to tell me, because it's not hydrogen...
It's maybe not a star. Well, it's not a very good fusion reaction, shall we say.
It's a star, but it's not a very good star.
They're very faint. They're very, they're small. Where is the line between what a Jupiter-sized planet is and a brown dwarf is? Maybe it's this 13-ish, which is about where you start to fuse deuterium, but that's a bit hazy. So again, okay, we've already run into problems with stars.
Right. So we're in this grey hazy, or this brown hazy area of... the fringe limit of what is stardom and what is just big planetdom.
Yep.
And okay, fine. All right.
Okay.
So we understand most of what
But we
stars
might
are.
be able to put a definition in there one day at least.
Okay.
But there's hope.
Yeah, we're pretty close.
Okay.
So that's the good one, you're telling me?
Yeah.
Where do we go from there?
So planets we've discussed,
Yep.
at least in our solar system.
Yep.
We're very confident we know what a planet is in our solar system.
Well, good.
Other exoplanets, tricky, not sure. Then we have in our solar system dwarf planets.
Of
So
which Pluto is
Pluto.
infamously one.
That's sort of reasonably well defined. Now, then, if you go smaller than that, the Venn diagram of stuff in our solar system, no, there is actually
Who doesn't love a good Venn
there's
diagram?
a wonderful big Venn diagram. It's actually an Euler diagram, and you have all these bits of stuff. So you have comets, you've got trans-Neptunian objects that we talked about last time. You've got bits of all these kind of little bits of lumps of rocks of things,
Asteroids and
all the little stuff. All of those definitions overlap in weird and wonderful ways.
excellent. And so what any given bit of stuff is potentially up for debate depending on who you're talking to and when you're talking to them.
Yeah. And what context they're looking at the object in.
Good. Well,
So
that's
that gets
working
really
well.
messy down there. So let's
Yep.
just totally ignore that
Okay.
end of the scale.
Okay, so that's
because
the
it's
messy end.
really
So we've got
messy.
stars, which we pretty much have, and we've got lumps of rock, which are just complicated. And in the middle, we've got planets, which are pretty good as long as they're close to home. And don't talk about exoplanets. And then moons?
Yeah, so moons. We can start with a good start with a moon. It has to go around a planet.
Okay,
That sounds like a good start.
sure.
A moon has to go around a planet. And it needs to be a natural satellite.
As opposed to something that we've flung up there. So the Hubble Space Telescope is not a moon.
No, it's
Right.
not a moon. Not allowed to be a moon.
Yeah, the ISS is not a moon.
No.
No, it's a satellite.
But the moon is a moon.
But the moon is a moon, hence the name. Well done there. For once, astronomers got the naming right.
We did
okay.
it. We did it good. Now, where do you can have big moons? We're fairly confident we know the moon is a moon.
Mm-hmm.
The two objects that go around Mars, Phobos and Deimos, the moons. Okay, that's kind of sensible. Jupiter, Saturn, they have lots of stuff going around them.
Like dozens, hundreds.
Well, yeah,
Many.
yeah, tens at least of moons, what we tend to call moons. But where does the limit stop between moons and bits of rock and ice that become rings?
Yeah, I mean, well, I was about to say Saturn, but Jupiter's got rings as well, hasn't
Yeah.
it? It's not nearly as prominent and as exciting as Saturn's, but they're there.
They're there.
And so, yeah, you're right. When is it a moon, and when is it a smaller lump of stuff, and when is it like melding into? Well, no, that's actually a ring of stuff now.
So people that study things in Saturn system have a definition, or maybe not a very defined definition, but an idea of these objects that are called moonlets.
Moonlets, good,
Which is
excellent. So we're
somewhere-
taking the concept of moon and just, well, if we add a little diminutive on the end of it, no one will notice, and we can all just move on with our lives.
And they are really important and super interesting. They do wonderful things like create gaps in the rings. They shepherd the material in the rings around. But yeah, common sense again, kind of, you see an object and you can maybe put it in a box, but actually
You know it
writing
when
a
you see it.
definition is
Yeah.
super hard. And I think we've just lost the faith of our audience into all of this.
Look, trust us, we do know what we're doing. We really do. Keep funding us. So,
But again, we're not talking about the small end of the scale here with
No,
this
okay.
system. Okay, so we're talking about two enormous things.
yeah, so in this particular one, getting back to the original story, we have an exoplanet around some distant star. The best model that we've got for what's happening there is that it's big honking planet with really big moon, like Neptune-sized moon. So on one hand, there's no denying that if that is what's going on, it's a planet with a moon. This is not a moonlet. It's not a ring. Like, let's take for granted that the model is right. But coming back to the question which came up earlier is it a moon? Or is this two planets?
Yeah, is it a binary planet? That was my question I asked myself when I read this article. And then I sort of thought, well, what is a binary planet? So coming back to the word binary, we use very often in stars. We know what a star binary is. You've got two stars that are orbiting a common place, right? A common center of mass, it's called. And this is like the point in space that the two objects go around each other.
Now, just to be clear, I mean, that's true of everything, right? The moon going around the Earth. Actually, the Earth is also, in a sense, going around the moon. I mean, gravitationally, they're attracted to each other, but they're actually orbiting around a common center, not the center of the Earth. The Earth is doing a little wobble around a different point, partway between the Earth and the moon, aren't they?
Yeah, yeah. So then that's true for stars. And
Yep.
when you have two stars that are similar in mass, then it's like about halfway between the two stars. So that, I think, is a useful starting point for thinking about this. What's wonderful about stars is that we know that at least half of all stars in our galaxy are in these binary systems.
Yeah, they're really common, aren't they?
Super common.
That it turns out that just having a star like the sun with a bunch of planets going around it is, I mean, it's normal, but it's not the only way that things can happen. The whole Star Wars thing of the two suns rising in the west might actually be very common.
I think it's true for someone.
Yeah.
And you can get binary binaries.
Sorry?
So you can get two stars that are orbiting each other, another pair of two stars that are orbiting each other, and then you can take each of those pairs and make those pairs orbit each other.
So you've got a binary system of binaries, each all orbiting. So you've got two sets of two orbiting around a common center for the lot of them.
Yeah, so four stars in total.
That can't be stable, surely.
No, it is. It is.
Really?
It really is. And I think we're up to 7 stars doing this kind of systematic orbiting in pairs, basically. Well,
That's
it's
crazy.
7. There's got to be one on.
I mean, presumably we can get threes as well then. You could get a binary with another single star. Or is that...
Yeah, well, a trinary. So what happens there is you get two orbiting each other, and then you get a third planet, a third star, in this case, that's orbiting the pair, as if they were just a single object.
So here's a question. Can you have, like if you had a big star and you had a little star in a binary, then if the center of that orbit is inside the big star, like it is for the Earth and the Moon, right? Is that still a binary star system? Or is that the smaller stars a bit like a planet?
It's still a binary star system.
Okay.
So we don't use the center of mass to define what a binary is.
Okay.
I mean, stars are kind of, if we see two stars and they go around each other, they're binary.
Okay, so for once we've got a fairly simple definition. Is it two stars? Well done. Fantastic. Excellent. That's a binary system. Okay, so that's binaries. We're getting a good sense of the definition of binary here. So let's now apply what we've just discussed to this system, this exoplanet, exomoon system, where you've got two big honkin' things. Is it
herein lies the problem.
Is it planet and planet?
We can define star pretty well, so we know when two stars are orbiting. But now we've got this weird twilight zone between a star, and a planet, and a moon. So is the Neptune-sized thing, which I should tell you its name because it's got a very... It's called Kepler 1652bi.
Okay.
B being the planet, I being the moon.
Oh, okay. You start counting I and then I and then I.
I don't think we've reached that point, but probably.
If we ever get there, that'd be fun. Okay, cool.
It's kind of
so
like,
that's interesting naming
like when you
system.
make bullet points in a Word document and you just keep going down.
Keep tabbing in. Keep tabbing in. Right, so we've got BI.
If it was going around the star on its own, it would be an exoplanet. Right. But it's not. It's going probably around the thing. So is a planet or is a moon? That's where we're running into troubles here.
Question. We know that binary star systems exist. Do binary planet systems exist? Like, is this a question which has come up before and we can compare it to another situation? Or is this brand new, hot off the presses? Here's an astronomical conundrum that we've never faced before. Actually,
it is a question that's come up before. And it's come up in our solar system because we have a pretty interesting pair, which are Pluto and Charon. And it's been discussed whether they should be called a binary dwarf planet system.
Okay, so Charon is one of Pluto's moons, at least in the old parlance, but they're comparable in size?
They're much closer in size than most other planet-moon systems. So to give you... Let's come back to the center of mass thing, because this is so important when we're thinking about... Well, it's one way we could define, for example, these binaries. The balance point is the tipping point, right, between these two objects. It's the same as if you were to balance a stick on your finger. You find a point where the thing balances. That's the center of mass of the stick. Your center of mass is somewhere in about your belly button if you want to balance.
if you were so inclined. Yep.
On a stick. Maybe don't do that. So Pluto-Charon is really interesting. So the center of mass is located about 2,100 kilometers away from the center of Pluto.
Right. So it's outside of Pluto.
Yeah, because Pluto only has a radius of 1,150 kilometers.
Right. So it's significantly outside.
So it's nearly twice Pluto's radius away. So it actually, this is one of the rare systems where the center of mass sits outside of the planet or the dwarf planet. To compare, so say our Earth-Moon system, we are looking at the center of mass is about 4,700 kilometers away from the center of the Earth, but our Earth is 6,000-ish kilometers in radius.
Okay, so it's quite a long way away from the center of the Earth, but it's still comfortably inside the bounds of the Earth's surface.
Yeah, and this is one of the reasons why the moon has such a huge effect on the Earth, right? Because that center of mass, if you like, moves as the moon orbits the Earth. So it changes these pressures and so on inside
and plays
the
with the tides and our moods and all sorts of fun things.
Yeah, werewolves. I mean,
so you're saying we do have a precedent in at least with dwarf planets that Pluto being demoted, we don't have to talk about it as a planet anymore. We have a dwarf planet, but if we've now got a dwarf planet and it's got a moon where the center of mass is outside of Pluto itself, then probably makes sense to call this not dwarf planet and moon, but binary dwarf system.
Yeah, that's one idea. And I thought, okay, that sounds pretty reasonable. And then I come back to the idea that we talked about for stars. Well, you don't do that for stars. Even if the star is really big, you don't say that the other star is just a dwarf star or, that is a different meaning. But yeah. But let's come back to our case because I did the maths because I thought, let's see.
Okay.
Let's see what this system is like. So we've got Kepler 1652b and 1652bi. The center of mass, and this is a back of the envelope kind of wish calculation, sits at around 16,000 kilometers away from the planet, Jupiter size thing.
So are you talking about away from the center?
The center of...
But what would be the radius of the planet? Is that inside or is it outside?
Wow, the radius of the planet is probably around 70,000 kilometers.
So it's happily inside the big Jupiter-y planet.
Yes.
Which suggests that even though the other lump of stuff, big though it is, Neptune size, it suggests we could comfortably still call that a moon.
But would you have looked at it and common sense said it's a binary planet?
I don't know. Common sense disappeared out the window about half an hour ago in this conversation, I think, Emily. So I'm a bit uncomfortable just appealing to common sense at this point. We need more than that. We need someone to tell us.
Okay.
Someone's got to make a definition. I want you to make the call, Emily. Is this a moon or is it a binary planet system?
I'm going to go with the authors here and say this is a moon.
Okay. I like that. I've got one last question then for you.
Yeah.
Given that this moon, which you have just defined, if it's that big, if it's Neptune size, something that's Neptune sized could have a moon. So could you have a moon around a moon?
Now that is an amazing idea.
Isn't it? Isn't that a good question? And it actually turns out that this has been asked. This has come up and there's a name for it. There is actually a name for this.
There's a wonderful name for it.
A moon going around a moon is a moon. Isn't that awesome?
We're going to get so confused.
I love that. A moon.
A moon.
So could you have a moon?
There's no reason why you couldn't. You'd have to have quite a well-separated moon from its host planet.
So the moon would have to be, and then the moon. So to give the moon enough room to go around the moon, the moon's got to be far enough away from the planet.
Yeah, and we've done models and simulations, and it kind of. If you get the right masses, the right distances, then you can make it work.
I mean, look, in principle, it's no different gravitationally to the Earth and the Moon going around the Sun. You've got three objects there. Big Sun, smaller Earth, smaller Moon. Here we're talking about planet, smaller Moon, smaller Moon. There's in principle no difference, but you're squeezing everything together a bit more.
You're just scaling it all down.
So presumably, as things get smaller, there's just a greater chance that, for example, the big Jupiter-y planet drags the moon away from the moon and turns it just into another moon. My head hurts.
So is it moons all the way down?
So, Emily, all right, I'm just trying to pull this around to some kind of conclusion here before my brain explodes. Are we likely to get any more certainty about this? At the moment, as far as I can tell, we've got some really good data from Kepler and then Hubble. We've got a bunch of models which point towards it might be a planet with a moon. There's no moons yet, so we'll just leave that aside. Is there likely to be any further resolution to this, or is this as good as we've got until we find other examples? Where are we? Help me out.
Well, the wonderful thing about systems like this is that those objects will continue to go around their host star.
Right. Yes, of course.
And they will transit again.
Okay. And so when's the next one?
It's on October the 29th.
What, this year?
This year.
Wow. Okay.
You know, it was going to do it at least once every year because it's got 280 something day orbit.
Of course.
So, yeah, we've got more opportunities to follow this up. And the more we know what, like, say we know what two models we're trying to distinguish between, the more we can tailor those observations and try and really nail the data in particular areas of that transit curve.
So we could have a little bit of an update on this. I mean, I'm guessing it'll take a little while for them to take the data and process it, but I don't know, when? Later this year? Next year?
Probably next year, yeah. I think this is kind of the discovery, if you like, of a maybe exomoon. I would not expect it to take very long before we get a real exomoon. Full on, yes, we've got it within the 99% confidence interval.
I want them to find a moon. Do you think they'll find an exomoon?
No.
Well, that's all the time we've got for this particular silly episode of Syzygy. If you've enjoyed what you're listening to and you want to get in touch with us, there's a whole bunch of different ways that you can do that. Emily, how can people get in touch with us?
Well, we're fantastic on Twitter. I can do the Twitter.
We can do the Twitter. We can't define things, but we can do Twitter. Yeah. How do they find us on Twitter?
So we're at Syzygy Pod, SYZYGY. And please do send us questions. Don't ask us how we're going to define planets and moons and things, but ask us other questions.
Ask us things that we can answer. that would help. If you send us through some questions, we will devote attention to them, and if we can find answers, we'll even include them in a future episode. There's historical precedent for that. We've actually done that before. So send us your questions. You can do that through Twitter. You can do that through Facebook.
Yeah,
you can go to facebook.com/SyzygyPod or just search for Syzygy Podcast on Facebook. That's how that works. Or you can just go to our website, syzygy.fm, and go to the contact form there.
A very nice looking website, I have to say, Chris.
It's looking nice. It's where all the episode show notes and everything goes. You can find all the past episodes on there and all the different ways that you can subscribe to the show on your podcast player of choice. If you like watching your podcast, you can find us on YouTube as well. Just go to YouTube and search for us. If you want to support the show, there are a number of different ways you can do that. Tell your friends, tell your family, go and leave us a review on your podcast catcher of choice, and go to patreon.com where you can become a patron of the show. You can actually contribute financially to the running of the show and help us to do bigger and better things in the future. As ever, we're recording Syzygy here in Emily's office at the University of York, who are very kind to lend us Emily from her normal day job to record the podcast. So we're very grateful to the university there.
So, Chris, can we choose an easier topic for next week, do you think?
Probably not. I don't know. Got any ideas?
Well, I thought black holes might be a good way to go.
Easier? Yeah, sure.
Easier than defining a planet, let's say.
Why not? Because, what could possibly go wrong with us talking about black holes? Until then, we'll see you next time.
See you later.